So we're going to start the session on deep learning, NLP, vision, and probabilistic methods in a couple of minutes now. So can I please ask everybody standing at the back or near the entrances to please take a seat? We have plenty of seats available. Thank you.
Still wait for a couple of seconds.
Okay, I think we should start things off. Welcome everyone to the session on deep learning, NLP, computer vision, and probabilistic methods. We're going to have 2 oral talks in this session and also 12 spotlight talks. We'll start with a batch of 4 spotlight talks followed by 1 oral, and then another 4 spotlight talks, another oral, and then round it off with a last set of 4 spotlight talks. So without further ado, let me introduce Octavian Ganea, who's going to tell us about hyperbolic neural networks.
Thank you very much. Hello, everyone. I'm Octavian, and today I'm going to present hyperbolic neural networks. This is work done together with my amazing collaborators, Gary and Thomas. So our goal is to use hyperbolic space instead of the Euclidean space to better represent data, and especially data with hierarchical structure. So what's good about this space? This non-Euclidean geometry provides a mathematically better way to embed tree-like graphs. So in order to see it at a very intuitive level, the volume of a ball grows exponentially with its radius in this space. So in this picture here, every bed has equal area. This is the same as for a tree. The number of nodes in a tree grows exponentially with the tree depth. So in the Euclidean space, at some point, you will run out of capacity, or you will have to increase your dimensionality exponentially in order to fit this, but not in the Euclidean space, where 2 dimensions are enough. So this is a hot topic in machine learning since the work of Nickel and Kiela on Poincare embeddings. So there remain a few difficulties in order to properly use this non-Euclidean geometry. The first question is how to use hyperbolic embeddings in downstream tasks. And a more specific, how to feed hyperbolic embeddings in neural networks. So this is difficult because basic Euclidean operations are not defined in the hyperbolic space. So for example, vector addition should follow hyperbolic straight lines or geodesics. And second, neural networks should not ignore the hyperbolic geometry. So for example, if you are dealing with recurrent neural network with the ones that hidden states are living in this hyperbolic space. So we are using the Poincare ball as a model of hyperbolic geometry. And what's good about this model is that we have access to closed form expression of some important quantities, like, for example, the distance function. So in our work, we rely on the zero vector space framework to generalize basic operations and neural networks in the hyperbolic space. So this framework it provides an analog of Euclidean vector spaces, and it comes from, it has strong connections with relativity theory. So vector addition, scalar multiplication, distance function, and geodesics have closed form in this framework. Our contributions are the following. So we first connect zero vector space framework and Riemannian hyperbolic geometry, and we obtain closed form expression of important quantities like exponential map and parallel transport, which can be used, for example, in optimization. Second contribution is to generalize fit-for-all neural networks to the hyperbolic geometry. And we do this in 2 steps. First, we generalize point-wise nonlinearities via this formula. And second, we generalize matrix vector multiplication. So these tools have important properties, for example, matrix associativity. Third contribution is to generalize multi-class logistic regression or softmax layer. We do this in a few steps. First of all, we generalize the notion of separation hyperplane or a hyperbolic hyperplane. And in our paper, we derive a closed form expression of a distance between a point and a hyperbolic hyperplane. Finally, based on previous work, we generalized the MLR formula, and we obtain a closed form expression that can be also differentiable. We can backpropagate through it. Last contribution is to generalize recurrent neural networks, and especially gated recurrent units, such that hyperbolic, for example, hidden states lie in the hyperbolic geometry and they respect this hyperbolic geometry. We do this in a principled manner by generalizing the update gate mechanism via a principle which is called the time wrapping invariance principle, and we use this by generalizing the chain rule to the zero vector spaces. An important property of all our models is that they recover their Euclidean variance when the space is continuously deformed to a space of curvature 0, which corresponds to the Euclidean space. Finally, we use Riemannian optimization since we have a full Riemannian optimization since we have closed form expressions for exponential map and Riemannian gradients. In a set of experiments, we outperform all the Euclidean baselines on textual entailment tasks, both semantic and syntactic, and also on classification of subtrees of the WordNet tree. So this is just basically done on pre-trained hyperbolic embeddings. Here I show on the left and the right side hyperbolic and Euclidean hyperplanes in 2 dimensions. Thank you very much, and please visit our poster number 29 and our blog, hyperbolicdeeplearning.com. And yeah, thank you very much.
Our next speaker is Elad Hofer, and this paper is titled Norm Matters: Efficient and Accurate Normalization Schemes in Deep Networks.
Which one is? Oh. OK. So hello, everyone, and thanks for inviting me. I'm Elad Hofer, and I will present Norm Matters: Efficient and Accurate Normalization Schemes in Deep Networks. This is joint work with Ron Banner from Intel and Itai Golan and Daniel Sudri from Technion. So batch normalization has been an important building block of deep learning models over the past few years, allowing faster convergence and improved accuracy. However, it is known to exhibit several shortcomings. Amongst them are the reliance on independence between samples, making it unsuitable for several tasks, such as RL and metric learning. That it has visible yet poorly understood interactions with other organization techniques. It also incurs noticeable computation and memory impact, accounting for up to a quarter of computation time, and it requires high precision operations, making it numerically unstable. One property of batch norm which we'll use is that of norm invariance. Given an input x, a weight vector w of the preceding layer, and its direction w hat, it is easy to show that the batch norm is norm invariant. This means that the norm of the weights has no impact on intermediate activations. We derived an equation for the change in the weight's direction. The only effect of the weight's norm is scaling the rates of these updates. We believe norm invariance is the main property leading to the success of batch norm, by explicitly removing the effect of the weight's norm. First, we would like to understand the interaction of batch norm with weight decay. We showed that using weight decay on layers preceding batch norm is equivalent to learning rate scaling and can be mimicked by simply adapting the learning rate. We recorded the norm of the weights trained with weight decay and then retrained without it, modifying the learning rate to account for the change of the norm. As you can see on the graph, we were able to replicate the results obtained by weight decay with this simple learning rate modification. One appealing alternative to batch norm is weight normalization, normalizing the weights instead of activations by decoupling their norm for the direction. It is more efficient than batch norm as it requires less computations, and more suitable for many tasks as it has no assumption over the samples in a batch. Unfortunately, weight norm performs much worse than batch norm for large-scale tasks, such as ImageNet. Understanding that the norm of the weights matter, we suggest fixing the weights norm in weight normalization in a manner similar to common initialization heuristics. As you can see in the figure, we were able to improve weight norm substantially in large-scale setting, where it previously failed to compete with batch norm. In batch norm, we subtract the mean and divide by the standard deviation, which is just a scaled L2 norm of the centered inputs. If, as we suggested, norm invariance is the main property of batch norm, It is not essential to use the L2 norm. Therefore, we can choose more stable norms, such as L1 and L infinity. These norms are easier to compute, usually require less memory, and do not suffer from numerical problems of regular L2 norm. To find the correct scale factor for each norm, we require that the scaled norms would be equal in expectation. To analytically calculate this expectation, we make the common assumption that the neural inputs are approximately Gaussian. Thus, for example, to use the L1 norm, we need to scale it by a square root of pi over 2, which is approximately 1.25. We additionally checked and verified empirically that this is the optimal scale needed. Surprisingly, this small constant makes a large difference. We can see on the left that a scaled L1 normalization, marked in green, allows us to use L1 as a drop-in substitute to regular batch norm without any additional modification. On the right, we can see that this leads to the same performance as batch norm on common models of ResNet 18 and ResNet 50 over ImageNet, allowing faster computation and smaller memory footprint. Replacing L2 for L1 also allowed us to alleviate low precision difficulties of batch norm, and we were able for the first time to train ResNet 50 completely in half precision without any modifications. With a few more tricks, we were able to use these ideas in a follow-up work, also available at NeurIPS this year, allowing training models in 8-bit of precision. We invite you to check our work, Scalable Methods for 8-bit Training, for more details. Thank you, and see you at our poster number 27.
Our next speaker is Yunho, and this paper is titled Constructing Fast Networks through Deconstruction of Convolution.
Thank you. Hi, everyone. My name is Yunho Jeon from KAIST in South Korea. I'm going to talk about my paper. The title is Constructing Fast Networks through Deconstruction of Convolution. Convolutional neural network has achieved great accuracy in many computer vision applications with deeper and wider networks. However, they consume more memory and time and cannot be applied in some environment. So our goal is to make a fast network and with good accuracy. Then how can you make a fast network? First, we can think of reducing computational complexity by using grouped or depth-wise convolution. Or we can apply network pruning also. However, low props does not guarantee a faster speed because of memory access. So we should also consider about the efficiency of the memory access. Here are the two strategies. First, reduce the memory access itself by removing spatial convolutions. And once the memory is accessed, it should be utilized for many calculations. It can be done by computationally dense operation like one-by-one convolution. To achieve this goal, we deconstructed spatial convolution into atomic operations. Here is the insight of the deconstruction. When you change the order of the calculation, spatial convolution is actually the summation of one-by-one convolutions with shifted filters. And then we can shift inputs instead of using these shifted filters. And then spatial convolution can be expressed as shift function and one-by-one convolution. Based on our understanding, if we can share these shifted inputs, the computational complexity and the memory access will be greatly reduced. However, if inputs are shifted only one direction, the expressive power is very limited and we cannot achieve a good accuracy. So the key challenge of this problem is the way of shifting inputs for better accuracy. Here is our approach called active shift layer. First, we apply the depth-wise shift, which means every input channels are shifted to different directions. For this, we introduced new shift parameter, alpha and beta, for each channel. And then we expanded them to real numbers by using interpolation of nearest 4 neighbors. This enables shift values differentiable and runnable, so they can be optimized through network itself. Here is the example of the distribution for trained shift values. The value rather than 1 can simulate a dielet convolution, and the receptive field of the network is enlarged by using these shifted inputs. This is the experimental result on ImageNet. Our approach achieved better accuracy with smaller number of parameters and runs faster with similar accuracy. For more information, please visit our poster, and thank you.
Our fourth spotlight presenter is Kim-In Lee, and he'll tell us about a simple unified framework for detecting out-of-distribution samples and adversarial attacks.
Hi, I'm Kim-In from KAIS. In our work, we introduce a simple unified framework for detecting out-of-distribution samples and adversarial attacks. This work is a joint work with Ki-Bong Lee, Hong-Lang Lee, and Jinwoo Shin. A classifier can provide a meaningful answer only if a test sample is similar to the training samples. However, there should be many unknown samples that classifier cannot give a right answer because it never saw them in training time. Such unknown sample causes critical concerns when deploying the classifier in real-world system. For example, consider an objective classifier for a self-driving car. If the classifier misclassifies some rarely seen item, a car accident might happen. However, if we can detect such unknown sample very effectively, it is possible to prevent the car accidents. Motivated by this, our goal is to design the classifier to say "I don't know" when the decision from a classifier is uncertain. Basically, this problem can be formulated as a one-class classification problem, which detects abnormal samples at test time by measuring some confidence score from a classifier. Here, the main challenge is how to define a confidence score for a test sample. In most applications, people utilize a posterior distribution from a classifier, py given x, where x is an input and y is its label. However, it is well known that the posterior distribution can be easily overconfident even for such abnormal samples. To tackle this fundamental limitation, we consider to model the data distribution px given y in this paper. This is because the px given y is a more direct metric to measure the confidence of an input x. To this end, instead of utilizing an expensive density estimator, we simply post-process a generative classifier on hidden feature space of a pre-trained softmax classifier. Specifically, we define class conditional Gaussian distribution on hidden feature space, where we estimate its parameter using an empirical class mean and covariance metrics from a training sample. Here, our approach is based on a theoretical connection that the posterior distribution of a generative classifier with a tied covariance matrix is equivalent to the softmax classifier. So we expect that training softmax classifier has some effects of fitting the hidden feature to Gaussian distribution. As shown in this figure, we indeed found that the hidden features of the network trained on CPAR10 dataset follow the class conditional unimodal distribution. So using this generative classifier, we define new confidence score as a Mahalanobis distance between a test sample and a closest class conditional Gaussian distribution. So in essence, we measure the log likelihood of a test sample using a generative classifier. Our experimental results show that the proposed confidence score outperformed the state-of-art baseline like ODIN and LID for detecting adversary samples and out-of-distribution samples. So let me conclude this presentation. Deep generative classifier has been largely dismissed because the deep discriminative classifiers like softmax classifier typically outperform for pre-supervised classification setups. However, in our paper, we found that deep generative classifier can outperform the softmax classifier across multiple applications, including detecting out-of-distribution samples and adversarial samples. Actually, there are more stories in our paper, including calibration techniques, applications, and evaluation. So please come to our poster session today for more information. Thanks.
Our first oral talk of the day is discovery of latent 3D key points via end-to-end geometric reasoning. And Supersorn Suvajanakorn will present this talk.
Terrific. Sorry, it doesn't show. Okay. Hi, I'm Supersorn from Vistech, Thailand, and this work is done with Noah Snavely, Jonathan Thompson, and Mohammed Norozi from Google. Being able to find semantic correspondence, such as these key points, is part of object understanding and is crucial in many vision applications. Humans are surprisingly good at this task, but this turns out to be very hard for computers because these chairs look very different, and not to mention that we view them from different angles as well. For example, to correctly identify or mask these red points, one has to know which parts are the legs and then understand the orientation of the chair to be able to pick the right leg. Now, what if we ask to pick 10 points? How do we decide which 10 points to pick? Sometimes we can reason about it. For example, we probably don't want to pick the armrest because the other chair doesn't have it. But in general, this is very hard. And it's not quite clear which points will be the most useful for downstream tasks. In this paper, we present an end-to-end geometric reasoning framework to learn an optimal set of key points along with their detectors. Given a single 2D image, our model extracts 3D key points that are optimized for a downstream task. The resulting key points are semantically consistent across viewing angles and object instances, and can be discovered automatically without any key point supervisions. Traditionally, the pipeline for geometric reasoning tasks comprises two separate stages. First, we would train a key point detector based on human annotations, then use the inferred key points to predict pose or viewing angles, for example. The first part requires expensive and error-prone key point annotations. So recently, people have been trying to learn key points in an unsupervised manner so that we can avoid collecting labels. Most of the recent work often uses an auto-encoded objective and a reconstruction loss to infer latent embeddings of objects. There's a lot of excitement around these techniques in computer vision and machine learning communities. People also have succeeded in learning key point detectors such as LearnSIFT, but so far only in isolation. The problem with that for geometric reasoning is that we never know whether the key points that we have are actually good for the task we're interested in. So in contrast to recent work, our main novelty lies in the use of end-to-end geometric reasoning to learn latent key points. That is, our key points are optimized with respect to a downstream task, rather than being learned through a proxy objective, such as reconstruction. And we use the post-estimation problem as one example of the geometric reasoning task. Here are our automatically discovered key points on test chairs from the ShapeNet dataset. Note that this is a frame-by-frame key point prediction using no temporal information. It can also track key points even when they're occluded. And unlike most work, we represent the transformation using real physical 3D transformation and predict key points in 3D. That allows us to match correspondence between two views that are 180 degrees apart that share no visual overlaps. What's surprising here is that the network tends to select key points that have semantic meanings that humans would tend to pick as well. For example, it picks the wheels of the cars, the cockpits of the planes, or the legs of the chairs. And here's how we train our network. Given two views of an object, our goal is to find key points that are best for estimating the relative rotation between them. Here, we pass the two images through our key point net that outputs a list of key points. From the two sets of 3D key points, we solve for the relative rotation between them via least squares by solving a problem known as orthogonal procrustes. Solving this problem requires computing an SVD, and so what makes this work is the fact that we can differentiate through the SVD operation. And this is the key component here. The loss is then the angular error between the estimated rotation and the ground truth rotation known during training. Another important loss is called multi-view consistency loss, which enforces the transform key points from one view to be close to those from the other view, and vice versa using the inverse transform. Now, let's think about architecture a little bit. Ideally, the goal of key point is to have a complete 3D transformation equivariance, but we haven't figured out how to achieve that with our neural net architecture, or whether that's possible at all. And so, however, what we can easily achieve is 2D translational equivariance. In other words, if the car moves to the right by 1 pixel, the key point coordinate should also change by 1 unit. And this can be done by instead predicting a probability distribution map for each key point, whose expectation represent the key point coordinate. And second, this requires no strided or stride-1 convolution. And in our case, we use a stack of dilated convolutions to increase the receptive field size. There are a few challenges with unsupervised discovery, such as when the object looks very symmetric like this car. In this case, the network could get stuck in a local minimum where it cannot disambiguate between the two symmetric sides of the car. So one trick that we found works well to help break the symmetry during training is by employing a coarse-to-fine prediction scheme. And one solution that we use is to have the key point net first predict an orientation flag, which says the car is facing left or right, and then condition the key point prediction on this flag and the original input image. This helps the network to track points all the way around the object. There are other generic key point properties that are universally useful for downstream tasks. For example, we don't want two key points to occupy the same spot. And we can prevent this by penalizing points that are too close together or points that are closer than a predefined constant delta. Another preferable property of key point is that they should lie on the object silhouette. And this is done by forcing the distribution map to be within the object mass known during training. We also want the distribution map to be peaky so that its expectation lies within the object in case of a non-convex shape. And this is done by minimizing the variance of the distribution map. For this work, we use ShapeNet dataset to train our network. ShapeNet is a large-scale dataset of 3D objects consisting of around 50 categories and 50,000 unique 3D models. These models, however, have different topologies, and there's no correspondence information between any two shapes. Once trained, our network is able to discover and consistently track the heads, the cockpits, or the wings of the planes automatically. And here are failure cases on the bottom, which happen on planes with very unusual wing shapes. Here, the network is having a hard time knowing which direction is front. And here are results on cars. Take a look at the blue car in the bottom, where the key points flip direction. This happens because this car looks very symmetric across two axes. So the key points shown here are actually in 3D, and to confirm this and really visualize them, we reproject these key points back onto the 3D model. So these color key points correspond to the color sphere in the model. Here we show how the network is able to infer the sparse 3D structure of the car from just a single image. More importantly, if we use a supervised pipeline and human annotations based on Pascal 3D, we get this mean and median error in the relative pose estimation. But our pipeline using zero key point supervision produces lower angular errors in the test objects. We also evaluate other metrics such as how consistent the predicted locations are by computing the standard deviation of the location. So ideally, this column should be close to 0. And our method also outperforms the supervised baseline and predicts more spatially consistent key points on all 3 categories. And here are the error distributions of the 2 techniques. Notice how errors are more concentrated around 0 for our technique. And there are a few outliers at 180 degrees due to the incorrect orientation prediction. Here we show how the model is able to predict key points from any angle consistently, even harder case such as from the side that causes a lot of occlusions for the plane. And here we want to see what would happen if we vary the number of key points. The network is very sensible here, and it starts by discovering the most prominent components such as the head and the wings, and then gradually tracks more parts as the number increases. And now, to make sure that the network doesn't cheat by just placing key points on a fixed rigid structure, we try our network on these following wiggly cars. So here, the network does use the local features to track parts and successfully predicts where the wheels are and the overall deformation of the car, of the object. To apply this technique to real images, we trained the same network, but with a random background taken from Sun 397 dataset. Surprisingly, such a simple modification works on some of the cars from ImageNet. And here we show a few handpicked results and some of the failure modes on the bottom. The network has difficulties dealing with large perspective distortion and cars with strong highlights or pattern. To conclude, we explore the possibility of optimizing latent key points through an end-to-end geometric reasoning framework by taking into account the downstream task. Our network predicts semantically consistent key points across viewing angles and object instances and outperform a supervised baseline on the task of pose estimation. And a few takeaway messages are that if you have a geometric reasoning task and you can differentiate through it and train it end-to-end, it can be quite effective and provides a pretty large performance gain. But if you can't differentiate to your task, or if your goal is to do unsupervised learning, you could still consider geometric reasoning as an auxiliary task. Because our world is 3D, and when humans pick up an object from a table and rotate it, we actually have the same kind of relative pose label from the manipulation of our hands. And this is exactly our problem setup. So this task could turn out to be very natural and fundamental, perhaps more than pixel reconstruction for unsupervised learning. Please visit our website for more details, code, and data, and poster number 33. Thanks.
Hello. Hi, this is a very impressive work. So
Thank
I
you.
just have very specific questions about propagating gradients through SVD. So one of the question is because when you're solving least squares, the SVD may give you superior solutions which contains reflections. So do you prune the singular values to rule out the reflection matrices? And secondly, propagating gradients directly through SVD sometimes is numerically unstable. So do you have special approaches to make it more stable during training? Thanks.
So the first question we did correct for the ambiguity either times 1 or -1. And for the pose estimation loss, in practice we actually add random noise so that it doesn't run into degenerate case.
Cool, thanks.
Yes, a very nice talk.
Thank you.
I had a couple of questions. Have you tried other data sets than ShapeNet and other downstream tasks than pose estimation?
So unfortunately, we only try on ShapeNet and then on real images, which is from also like a subset of ImageNet, Sun's UG, or Sun 397.
And other downstream tasks?
So this paper only considered the post-estimation tasks, but they could be other tasks like estimating the scale or the deformation object. Or the other non-geometric related would be how do you find the best key points for retrieving objects. That would be like a completely different objective, which could be the same framework could apply.
Thank you.
Thanks.
I have a question. Just a question. You show quickly some real images. Maybe you answered already. I don't know. How do your model separates the background from the main object? Right? So because all the key points were on the main object in the picture.
Oh, so the training for real images, we actually train on synthetic, except it's the same, except we add random backgrounds. So during training, we actually have a little bit signal of where the mask, where the objects are.
Oh, so you didn't do on the image build background.
Yeah, we train on synthetic,
Okay.
but with real backgrounds.
Okay, good, thank you.
All right, thank you.
Okay, with that, we begin our second set of Spotlight talks. Our first speaker in this set is going to be Kevin Ellis, and he'll tell us about learning libraries of subroutines for neurally guided Bayesian program induction.
Hi, thanks. So what we want to do is we want to make machines that learn how to program. And we want to do this without giving it example programs, and we also want to do it without giving it a powerful domain-specific language to start with. So we have a new algorithm called Explore, Compress, Compile, or EC squared, for accomplishing this task. And the way it works is by jointly acquiring two different kinds of programming expertise. The first thing that it learns is a library of functions that are tuned to a domain of problems. And the second thing that it learns is how to use those functions in order to quickly solve new problems in the future. We apply it to several different problem domains, and on the slide you can see example programming tasks from 3 domains. So for list processing, we're learning how to reverse a list. For text editing, we're taking some names and putting doctor in front of the last name. And for symbolic regression, we're looking at a curve and then writing down a function that describes that curve. So imagine that you had to solve the following programming problem from these input outputs. It's probably pretty hard to tell what's going on. But now imagine that I told you that you're starting with a library which has the following procedure. So you don't have to know what that Lisp code is doing like specifically, but you can think of it as like taking a list and a predicate and then getting all the elements out of the list or filtering the list whenever that predicate returns true. So if you have this in your library, then you could write the following piece of code, which just says take the input list and then filter all the elements that are bigger than 2. So if you take this EC squared algorithm and run it on a corpus of around 200 list processing problems, what it discovers are a bunch of sort of standard list manipulation routines, things like how to append lists or how to take the maximum element of a list. So you can think of EC squared as a hierarchical Bayesian model where at the top there's some latent library or DSL which generates programs which then solve programming tasks, which is what we actually observe. And we're also going to infer a neural network called a recognition model, which is going to predict a distribution over programs that are likely to solve each task. We have a 3-step inference procedure for this model. In the explore phase, we search for programs that solve tasks, and the way that that works is we take our task and we pass it to the recognition model, and that biases a search over programs written in the DSL, and we search for the ones that solve the task. Once we have programs solving tasks, we update our DSL in the compress step, and the way that that works is we analyze the syntax trees of programs found during exploration, and we pull out fragments and add them to our DSL. During the compile phase, we train a neural network to help search for programs. And the way that that works is we sample programs from our DSL, run them to see what they do, and then tell the neural network, when you see this task that you just sampled, predict the program that you also sampled. And the advantage of this is that you can draw as many samples as you want, training on a very large corpus of problems. And then we just repeat these 3 steps, explore, compress, compile, in a cycle. So I've shown you some of the list processing problems that we applied it to. Here are some text editing problems where you need to manipulate some strings. And we start the system out with things like map and fold, and then it has to learn a library of routines which allow it to edit text. So here are 2 text editing problems. And the way that it solves this is by learning routines for doing things like appending strings, and then it sort of builds on itself in later iterations. So it learns how to append strings, and then later it learns a routine for putting a string in parentheses, which uses append. So in order to learn programs with continuous parameters, what we can do is we can differentiate through the program and set those parameters using gradient descent. So we tested this out on some symbolic regression problems where you have to write some code that fits points on a curve, and we added the twist that the recognition model gets to eyeball a graph of the function so it can get a sense of what kind of code it needs to write before it starts writing it. Very recently, we've been looking at generative graphics programs where the agent sees a picture and has to write some code that draws that image. So here are 90 pictures that we trained the system on. One way of examining the learned DSL is to draw sample programs and see what kind of images they produce. So prior to learning, they're mostly like lines and simple curves, and afterwards there's a lot of rich geometric structure. We can also take individual DSL primitives that were learned and put into the library and run them with different parameters. And when you do that, what you see is that it's learned interpretable geometric drawing routines for things like circles and lines and polygons. So we think that this combination of learning a library of functions as well as learning a neural recognition model for searching for code is a way of making program synthesis more generally useful for AI. For more information, go to our poster. It's poster 24.
Our next speaker is Hanjun Dai, and he'll tell us about learning loop invariance for program verification.
Okay, thanks for the introduction. I'm Hanjun. This is a joint work with Xujie, Mukund, Meiyu, and Li. So program verification is about formally prove the correctness of a program. To achieve such a goal, typically one needs to apply a set of rules. While most of the rules can be deduced automatically, the while rule requires something called the loop invariant. And finding the loop invariant is equivalent to the halting problem. So in general, it is undecidable. So what is loop invariant? Given the program like this, which contains a single loop, the corresponding loop invariant is a logical rule that tells some properties about the variables. So this rule should satisfy 3 conditions, namely pre-invariant and post conditions. So basically, it says this rule should hold true before, during, and right after the loop. So fortunately, it is relatively easy to check whether the proposed loop invariant is correct or not using some automatic serial improvers such as these 3. So it is quite natural to formulate it as a bandit problem. The agent keeps proposing the loop invariant, and the checker tells whether the proposed one is correct or not. So one can see that positive reward is only received when you actually solve the problem. This is quite difficult for reinforcement learning algorithms because of the sparsity and the non-smoothness of the reward. Another interesting challenge is, suppose we have found the loop invariant for a set of programs. Can we gain some insights and find the answer for new programs faster? To solve the sparsity issue, let's take a closer look at the checker. So every time when the proposed solution is rejected, the checker will provide additional information that tells you why you are wrong by providing this counter example. So the counter example is an assignment of the variables. So as the interaction with the checker goes, one can collect a set of counter examples. Recall that the loop invariant should satisfy 3 conditions. So here we can collect 3 sets of counter examples. One way to use this rich feedback is to evaluate the proposed loop invariant against those counter examples. So using the fraction of the counter examples passed, you can interpolate the reward between 0 and 1 smoothly. And we'll only call the checker once the proposed loop invariant passed all the counter examples. This can further reduce the requirement of the Z3 calls. Okay, to solve the generalization issue, here we propose a graph representation module. So using the graph neural networks, one can get a transferable representation of the source code. Okay, this is like the overall framework of our proposed code-to environment. So in each step, the agent will propose a predicate, which is part of the solution. And in addition to the final smoothed reward we just talked about, we also added the additional intermediate rewards to guarantee the proposed predicates are valid. So to evaluate our framework, we collect a set of, in total, 133 benchmark programs. So each program contains a single loop with arbitrarily nested if-else branches. So we first treat the code to environment as an out-of-the-box solver. That means we associate a set of neural network parameters to each of the program instances. And we compare against a set of solvers from program language literature. In this figure, the green curve is ours. We can see that with a fewer number of these records, we can solve more instances. And we can also solve comparable number of instances within 1 hour time limit. And to gain a tiny step towards finding the generalizable solver, we add some confounding variables to get the permutation of the programs. That's how we can get the programs with the same underlying semantics. And in this limited setting, we can see that with proper pre-training, we can get a better sample complexity comparing solving from scratch. Okay, thanks everyone, and welcome to our poster this evening.
Our next paper is titled Deep Prob Log, Neural Probabilistic Logic Programming, and our speaker is Robin Menhave.
Hi, everyone. So I'm very excited to talk to you about Deep Prob Log, our research. So this was done together with Sebastian de Manchits from KU Leuven, Angelica Kimmich from Cardiff University, Thomas de Meester from UG Gent, and Luc de Raad from KU Leuven. So real-life problems often involve two important aspects. First, you have to do some symbolic perception, such as object recognition. Now, this can be solved using deep learning. On the other hand, you often have to perform reasoning with knowledge under uncertainty, such as knowing that you have to stop in front of a red light, but being unsure of what the car next to you is going to do. Now, deep learning might not be the best thing to use to solve this. Instead, you might want to use something like a probabilistic logic programming language, such as ProbLog, which was developed at our research group. So that's why we decided to integrate these two into Deep ProbLog, which is just ProbLog extended with a neural predicate. So what is a neural predicate? Well, imagine you have a classifier with a normalized output distribution. You can interpret this as a probability distribution. And it makes sense because often there's uncertainty in the predictions. Such in this case, your classifier might dial between a 1 and a 7, and rightfully so. So our neural predicate would then simply model the output of the neural network as a probabilistic choice in our program. And then we don't actually need to change anything about ProbLog, its inference, or its semantics. And thanks to the power of ProbLog, we can also natively calculate the gradient with respect to these probabilities. So the perception task is still solved by the neural network, while the reasoning happens in our ProbLog program. Now, the neural predicate is simply the bridge between both, taking the probabilistic output of the neural network and putting it in the program while still maintaining a clear distinction between both sides. So, of course, there has been related work on this field. However, often we feel that the logic has to be made less expressive, or it's pushed in the neural part, after which we have to try to retrieve it. And the fuzzy logic is used, and all of this together might sometimes lead to the language semantics being unclear. While in Deep ProbLog, we retain the full expressivity, we have a clean separation between both components, and we use a probabilistic logic, all of this giving us a clear semantics. So let me demonstrate this one example task. We changed the MNIST task to grouping multiple digits together into multi-digit numbers, and we label pair of these with their sum, so there are no singly labeled digits. Now, can we solve this using a neural network? Well, they're not extremely suited to do this, because it would be quite a hard task. Now, Deep ProbLog can solve this. How? Well, the neural predicate would go from pixels to distribution over digits. It's also important to note that Deep ProbLog can then train these neural networks from scratch. And in the logic, we will combine predictions to form the multi-digit numbers and perform the addition in logic. Now, to really demonstrate what Deep ProbLog can do and all of its possibilities, we decided to make a little experiment where you have to simultaneously train a neural network from scratch, perform probabilistic reasoning, and learn an unknown probability distribution. So we did this by playing a little lottery game in which you take some colored balls out of urns and flip a biased coin. So here our first task is to actually learn distribution of the balls in the urns and the bias of the coin. Now, we only give the program visual data. So there's also this task where you have to look at the balls and classify them according to their color, and also look at the coin and see if it's heads or tails. So that's our second task. And finally, we have to include the rules of the game and perform some logical inference to determine if we will win or not. So dProblog can do all of this entirely from scratch by defining a loss on the output probability and then working backwards, deriving the gradients, allowing us to train the neural networks and update the parameters of our own of our probability distributions. So to conclude, dProblog, it's neural probabilistic logic programming. It's the integration of deep learning and probabilistic logic programming. Because of the probabilistic aspect, we actually have a clear semantics and a clean separation between both components, allowing us to retain the power of both worlds. And thanks to the power of Problog, this was actually fairly straightforward to implement. Our code is also available online on the repository. So for the people going, well, this is nice, but what about the details? What about the little tables, lots of numbers? So I invite you to come to our poster. So it's poster 118 on the 5th floor, and to read our paper, of course. Thank you very much.
Before proceeding to our next talk, can I please ask some of those standing near the walls to please take up some of the empty seats here? The fire code prohibits people standing near the entrances. Thank you. So our next speaker is Kevin Ellis once more, and this time he's going to tell us about learning to infer graphics programs from hand-drawn images.
Thanks. So vision is very rich. We can infer objects and parts of objects and relations between them, but it's also very abstract. So for example, if you look at a spiral staircase, you can immediately perceive radial symmetry. Or if you look at trees, you see fractal-like structure. Or if you look at mechanical parts like gears, you see a lot of iterated repetition. And there's many, many examples of this. So how could we build machines with similar visual inference abilities? So as a first step toward this, we made a system which looks at a hand drawing and then infers a high-level graphics program describing that image, where that graphics program captures features like symmetries and repeated structures. So we have a two-phase pipeline for going from an image to a graphics program. In the first phase, a convolutional neural network looks at the image and then infers a collection of primitive drawing commands. These are things like circles and rectangles and lines, and they act as a specification or a spec of what the program needs to do. Once we have this specification, we use symbolic program synthesis techniques to infer a program consistent with the spec. And in order to make the search tractable, we also learn a policy that guides the synthesizer. In order to parse an image into primitive drawing commands, we combine two ideas. The first idea from attend, infer, repeat is to decode the objects in the scene one by one, focusing in on them using an attention mechanism, and then rendering them to a canvas on the fly as we decode them. The second idea from neurally guided procedural modeling is to wrap this all up in an outer loop that does sequential Monte Carlo, a stochastic search, over the space of parses of the image. To generalize to real hand drawings, we train it on a synthetic corpus of images that are rendered to make it look like they were drawn by hand. So if you just use the neural network, it does okay as long as you're not evaluating on scenes with way more objects than were in the training data. Here we train on scenes with up to 12 objects, and you really need the sequential Monte Carlo search in order to handle scenes with many more objects than were in the training data. Once we have the specification, we use constraint-based program synthesis to find a minimum cost program consistent with the spec. Here the cost function favors shorter or simpler programs. These programs have things like loops, simple kinds of conditionals, coordinate transformations, and arithmetic. So these synthesizers do a smart kind of exhaustive search, and they always find the exact minimum cost program, but they also can sometimes be very slow. So for our corpus of drawings, on a quarter of all drawings, they take over an hour. In order to make the synthesis be much faster, what we do is we learn a search policy to guide the synthesizer. So what the search policy does is it takes the entire space of all programs and then it chops it up along different axes. So for example, it chops it up into the short and the long programs, or the programs that use reflections and those that don't, or the programs that loop and those that don't. And then it tells the synthesizer how much time it should spend within each of these partitions. So if you don't use the policy, we end up taking around 280 seconds to synthesize a typical program. And then once you do use this learned policy, we can synthesize most programs in about 30 seconds. Here the times are plotted on a log scale, and it's a histogram of the frequencies of different synthesis times. Here are some example programs that we synthesize. In the top, you see affine transformations like rescaling. In the middle, you see reflectional symmetries. And at the bottom, you see a long, complicated program that uses nested loops and conditionals. One reason why you would want to synthesize a program is because it can correct errors made by the neural network. So the idea here is that the synthesizer can favor neural network outputs that lead to shorter or more naturally structured programs. This is a kind of top-down influence of symbolic reasoning at the program level upon the bottom-up perceptual inference being made by the neural network. Programs also support strong kinds of one-shot generalization. So here what we're doing is we're taking a hand drawing, inferring the graphics program, and then generalizing it by extrapolating it. The way that the extrapolation works is by increasing the loop bounds. So we think more generally that this two-phase pipeline is a way that you can integrate bottom-up perceptual inference with top-down programmatic reasoning. For more information, come to our poster on the second floor. Thanks.
Our second oral talk of the day is going to be about learning to reconstruct shapes from unseen classes. Okay. And this is going to be jointly presented by Jiutong Zhang and Xiuming Zhang. And Jiutong will go first.
Thanks. Good afternoon, everyone. We would like to introduce our work on learning to reconstruct shapes from unseen classes. This is a joint work with Xiuming, Chunkai, Josh, Bill, and Jiajun. So given a single image of an object, human can easily imagine the 3D shape of it, even if a major part of the object is not visible. One of the hypotheses behind this ability is that we learn to hallucinate the 3D shape of an object based on our past experiences. Instead of memorizing them, we learn to predict the 3D shape of an object based on current perceptual information. And such ability generalizes well even to objects that we may have never seen before. Recently, computer vision researchers aim to mimic such ability by training a neural network with large CAD model datasets and rendered images. More specifically, most past approaches fall into the general category of minimizing some loss functions between the predicted shape and the ground truth one. Since the mapping f theta is usually hard to learn, previous works have proposed different loss functions, learned priors, or extra supervisions to facilitate this process. For example, two very recent approaches, called DRC and AtlasNet, use different representations, loss functions, and training paradigms to approach this problem. On training classes, their model performs quite well. However, if the input image is not from their training classes, for example, a table, both algorithms fail to give reasonable explanations. And they give outputs that are very similar to their training classes. More importantly, both algorithms' predictions fails to explain the input image, which is not a desirable behavior. In some sense, such behavior can be viewed as a severe overfitting over the training classes, so a proper solution is to add regularizations to the function f theta. In our work, we show that introducing proper inductive biases to the mapping f theta is a very effective approach. Specifically, our choice of inductive bias is inspired by the forward image formation model. To take an image of the 3D model, one needs to first specify some camera and lighting setup. Given this setup, light rays emits from the light source, then hit the surface of the object and reach the camera. However, only the information of the visible surfaces reach the camera. Taking an image is then projecting these visible surfaces from 3D space to 2D image space. Given this two-stage process, we can design an inverse model accordingly. First, given a single image, we can first infer the 3D information of the visible surfaces by estimating its corresponding depth map. Then, we aim to complete this partial visible surfaces back to the original shape. This gives rise to one of our previous works, where we use two separate neural networks to first estimate depth information from a single image, then use another network to predict the final shape using the estimated depth. However, we observe that the second neural network, under such design, is always over-parameterized, as it has to implicitly learn a deterministic projection process, which is essentially parametric-free. As the depth image can always be projected into 3D space, we can explicitly perform this operation in a fully differentiable fashion and let the second network only perform surface completion in 3D space without having to learn this process explicitly. But we empirically find this approach problematic as the partial surface is very sparse in input space. It's very hard for the network to capture local surface features and to perform the job efficiently. To overcome this, we introduce a surrogate representation of 3D surfaces called spherical maps. The spherical maps are defined as projecting 3D surfaces onto a unit sphere. Specifically, given a sparse surface in 3D, we first initialize a UV discretized unit sphere around the origin. Then, for each UV coordinate, we shoot a ray towards the origin, record the distance it traveled till hitting the surface of the object. Through such operation, we encode the 3D surfaces on a 2D manifold where the surface information is no longer sparse. Using this representation, our proposed model, called generalizable reconstruction, short for GENRA, first predict the depth information from a single image, and then we use a deterministic projection process which converts the depth image into spherical maps. Then, we use another neural network to complete the object surfaces in spherical domain. However, as special spherical projections does not represent 3D surfaces in a lossless fashion, where regions of self-occlusion is always ignored. Therefore, to give the final estimation, we project the predicted full spherical map back into 3D space and use a third neural network to refine the self-occluded regions. This is an overview of our proposed model genre and its design motivations. Now Xiumi will elaborate on our training paradigm and evaluation experiments.
We like to highlight a distinction in supervision type crucial to generalizability, object-centered supervision versus viewer-centered supervision. With object-centered supervision, the model always learns to predict the 3D shape in its canonical pose, regardless of the input view. Take this table as an example. If our input view changes, the 3D shape supervision remains the same. In this case, the model is actually solving an easier problem where some voxels are consistently occupied or empty across different tables. As canonical pose is class-dependent, object-centered supervision is not suitable for generalization. This has also been observed by Xin et al. In this year's CVPR. In contrast, viewer-centered supervision requires the model to predict not only the 3D shape, but also its 3D pose. So if our input view changes, your supervision rotates accordingly. Although this makes reconstruction more challenging, we believe this is the right way to go for generalization, since canonical pose is not really defined for an unseen class. Before talking about generalization, let's warm up with objects from training classes. Here are the 3 single images and their corresponding 3D shapes. We compare with differentiable reconsistency, or DRC for short. It was trained using viewer-centered supervision, same as ours. We also compare with the state-of-the-art AtlasNet, which was trained using object-centered supervision, as it tends to predict unstable results when viewer-centered. AtlasNet here is able to reconstruct a stereotypical shape of the correct class, but lacks specific features present in the input view, such as the curvy chair base. Here are the reconstructions by genre. The left column shows genre reconstructions are view-aligned with the input images, which brings great advantage in generalizing to unseen shape classes, as we will show soon. Note how genre is able to preserve the specific shapes features, such as the car's top light, the airplane's engines, and the curvy chair base, by exploiting the only views available. We've also quantitatively evaluated how the three models compare using transfer distance, which is the sum of closest point distances between the reconstruction and ground truth. As these objects are from the training classes, the object-centered AliceNet exploits canonical poses, outperforming genre by 8%. But what about the novel classes that are never seen during training? Take sofas as an example. We are pushing AliceNet to a region where it's not designed to work, and indeed it doesn't. The L-shaped sofa got reconstructed into a chair. But our model is designed to generalize to unseen classes, and we see it does generalize to sofa, despite having never seen one. Notice how the sofa back, despite non-visible, gets reconstructed to be a smooth plane. How did genre do that? Completing a non-visible surface in 3D is actually easy in the spherical domain. The non-visible sofa back shows up as blank or missing values in the partial spherical map. And our impeding network then guesses the missing values in a smooth manner shown on the right. This operation basically completes the non-visible 3D surfaces. Here is generalization to bookcases, desks, and loudspeakers. Genre reconstructs shapes that correctly represent the novel task categories. Quantitatively, reconstructions by genre are over 26% better for these three novel classes. Here are more comparisons. Note how genre preserves the detailed structures visible in the input views. We further test genre on non-rigid shapes. As a reminder, it had seen only cars, chairs, and airplanes during training, which are all rigid shapes. For this experiment, we use depth as input. Genre completes non-visible parts of the human and the horse, utilizing generic shape priors learned from rigid shapes. Since our model preserves what is present in the input view, it's natural to ask how the input viewpoint affects generalization. So on this view grid, if we traverse horizontally, we are viewing the object from varying azimuth angles. Similarly, the vertical axis represents change in the elevation angle. Now we can compute the average reconstruction error for the novel class of tables as a function of azimuth and elevation, with darker colors representing larger errors. The view enlarged here is an accidental view from which we have no clue what the table legs look like. As the heat map shows, accidental views lead to large reconstruction errors. In contrast, the green view below reveals its legs. We therefore call this view generic. Reconstruction from generic views have lower errors, consistent with our intuition. We hope this heat map could highlight the importance of input views in the problem of single image 3D reconstruction. So in conclusion, what's cool and new here is genre generalizes to unseen classes. That means you can train your models on cars, chairs, and airplanes, and then reconstruct a 3D bed or 3D table from its image. We did this by imposing stronger regularization, using a more compact surface representation, and exploiting conditional independence. Thank you all for your attention, and please visit our poster for more.
We have time for a couple of questions. OK, let me start with one. Thank you for the very impressive work. And one question I had was, have you actually tried explicitly characterizing how well your model generalizes to new classes by, for instance, training your own model on the unseen classes and then comparing the performance? And which of the three stages of your pipeline would benefit the most, do you think, from being able to see the new classes?
Thanks for the question. So in the paper, we have done tons of ablation studies to evaluate different stages of contributions to the final generalization power. So we'll come to visit our poster, so we can give a more detailed explanation on the experiments. Thanks.
And I think I would also like to add to that question. So Essentially, I think the most important component here that allows you to generalize is really by reconstructing the object in its original view so that you could actually like project what is visible in the original image back into the 3D place. So this is one of the ways to ensure whatever you see is definitely preserved in the reconstruction.
Thank you, Jotong and Shuming. With this, we'll move to our last set of spotlight talks. We'll have 4 spotlight talks, starting with Richard Shin. Is Richard Shin here? Okay. Okay. Ilya Polusukin will actually present this talk, and the title is Improving Neural Program Synthesis with Inferred Execution Traces.
Hi, everybody. It's a joint work with Richard Shin and Don Song from Berkeley. So deep learning has becoming more and more popular to be used in program synthesis, specifically from input and output examples. And kind of a general trend is in research is to use inductive bias to improve how models learn. In program synthesis in general, it seems like execution traces of the program would be very useful for pretty much improving how models learn. Specifically, program traces provide way more richer context for your program synthesis problems. It definitely has more context on than input-output examples. They provide you with much richer kind of information about what's happening with the state machine, and it provides you context on how the state changes from elementary operations. So in this work, we're exploring a question, can we, instead of using explicit execution traces, which is hard to get from users, can infer execution traces from input-output examples and use these inferred execution traces to produce final programs. And on Carol domain, we find that this is true, and we receive state-of-the-art results both on simple and complex programs. And our hypothesis is that execution traces are providing a rich inductive bias for program synthesis problem. So the Carol domain pretty much is a programming language that is used to teach students programming in Stanford. It's a simple grid world with an agent that interacts with it. It has basic actions, some conditionals, for loops, and if statements. And the summary of our approach is a pipeline of 2 models. The first model takes input-output examples individually and produces traces for them. And the second model takes all of these traces together and tries to find a program that satisfies all of them. So diving deeper, the first model is input-output to trace. It's a pretty much convolutional model that encodes grid worlds of the input-output pair and uses LSTM to produce individual steps on a state. And we feed the actual state that you would achieve if you run the steps into the sequence model, providing a lot more context on how the state machine changes. The second model is trace to code, which now takes all of these traces from previous model and uses bidirectional LSTM to encode them. We still feed input-outputs as well, and we use LSTM to decode it, which uses attention to pick up relevant information from execution traces. So this work is following on Bunnell et al., which released a dataset, Carol dataset, with 1.1 million examples and 2,500 test examples. And each example contains a ground truth program and 6 input-output pairs. So the way we train this model is by taking all of the training examples by pretty much 6 input-output examples, training input-output to trace model, and then running it on the training data to produce inferred traces. And then trace to code model is trained on inferred traces, because if it's trained on gold traces, it actually performs worse, as it doesn't learn how to accustom for the errors in the previous model. And of course, for test purposes, we only give 5 input-output pairs, and we test on the 6th one. So here's a summary of our results. Specifically, we outperform across all metrics previous work. And the metrics we used, first of all, is exact match, which is exact token by token match with a gold program. It's a little bit confusing because there's a lot of possible programs that satisfy the input outputs. So there's a more general metric, which is generalization, that evaluates how well it generalizes to the 6 input-output example. There's also top 50, which is a beam search across all the programs. And we added a new metric, which is a guided search, which allows to pretty much use 5 given input-output examples to find the correct program and then test on the 6th one. And we also evaluate on different slices of data, showing that we outperform specifically on longer programs and more complex programs, which shows better generalization. Please stop by our poster at 31, and thank you.
Our next speaker is Hongzhou Lin, and his paper is titled ResNet with 1 neuron hidden layers is a universal approximator.
Hello, everyone. Today, I would like to show you our work about ResNet being a universal approximator. This is a joint work with my supervisor, Stephanie, at MIT. So let me start with the classical result. The study of neural network can be traced back to the 90s. At that time, people are interested in network with 1 hidden layer. And it is proof that if we allow infinitely many neurons in this layer, then we can approximate any well-behaved function. This is known as the universal approximation result. But now, we are using deeper and deeper networks instead of the fat ones. So a natural question is to ask, how does this result generalize into the deep learning setting? More precisely, how many neurons do we need in order to guarantee the universal approximation result? Interestingly, the answer depends on the architecture of the network. What we prove in our work is that using ResNet architecture, 1 neuron per hidden layer is enough. However, the story is quite different for fully collected networks. So here we show a very simple example to illustrate the difference between different architecture. So in this task, we perform a classification of the unit ball distribution. So the points inside the unit ball, the red points, which are the positive samples, the point outside the unit ball are the negative samples. So we first apply narrow fully collected network. By narrow, I mean that the neuron per layer, the number of neurons per layer is smaller than the input dimension. Since here we are in a 2D plan, the number of neurons is 2. So we train different neural networks with different depth, and we plot the decision boundary in the following figure. As you can see, the performance does not quite improve when we increase the depth. They are somehow just rotating between them. And maybe you can see that this is because we stuck in a local minimum or stationary point. But in fact, this is not the case. It is proved by last year's NeurIPS paper that the decision boundary of a narrow fully collected network is always unbounded. So we have no hope to approximate such simple distribution if even we allow the depth goes to infinity. So I emphasize that narrow means that the number of neurons per layer is smaller than the input dimension. Now the question is, how does this result change when we apply different architecture? So ResNet is a very popular architecture in practice. So basically, the main difference is that there is a skip collection propagating the identity from the previous layer to the next layer. Then we will apply ResNet on this simple example. Here we will apply ResNet with 1 neuron per hidden layer, which means there is only 1 nonlinear activation functions in each hidden layer, which are the green nodes. And on the bottom, you can see that the performance increases when we add more depth into the network. And we are getting better and better approximations of the unit ball distribution. So this motivates our theoretical work. The main contribution of our work is to prove that ResNet with 1 neuron hidden layers is a universal approximator when the depth goes to infinity. So if you are interested or have any question, please come by our poster at number 28. Thank you.
Our next talk is going to be presented by Lunjia Hu, and this talk is titled Towards Understanding Learning Representations, to what extent do different neural networks learn the same representation?
Thanks for the introduction. This is a joint work with Li Wei Wang, Jia Yuangu, Yue Wu, Zhiqiang Hu, Kun He, and John Hopcroft. Let me start with the motivation of this work. Deep nets work well partly because they are able to learn particular features or representations in their intermediate layers. And people have designed architectures in order to learn these representations better. For example, convolutional neural networks are designed to learn image representations well. However, there is a lack of theory on what these representations really are. There is one fundamental question that hasn't been answered. Are the representations learned by deep nets robust? In other words, are the learned representations commonly shared across multiple deep nets trained on the same task? In particular, suppose we have two deep nets with the same architecture trained on the same training data, but from different initializations. Given a set of test examples, we want to ask whether the two deep nets share similarity in their output of layer I. This question is trivial when layer I is the input layer because the similarity is high for both deep nets take the same test examples as input. When layer I is the final output layer, the similarity is also high, assuming both deep nets have tiny test error. So the real interesting question is how similar are intermediate layers, and do some groups of neurons in an intermediate layer learn features or representations that both deep nets share in common? And how large are these groups? In this work, we give a characterization of two groups of neurons learning the same representation. Let's look at these two neural networks. They have the same architecture, trained on the same training data, but from different initializations. We will focus on layer I and layer I+1. Let's look at these two groups of neurons. We say they learn the same representation if there exist linear transformations, A and B, that transforms the output of these two groups of neurons back and forth. To see why this definition makes sense, let's rewrite these two groups of neurons in this way, in this form of linear transformation. And we notice that each neuron in layer I+1 takes the inner product of the output of layer I and the weights. So we can move the linear transformation to the weights by adding a transpose. And if we do so for each neuron in layer I+1, we get two new neural networks where these two groups of neurons are swapped, but they still calculate the same functions. Therefore, in terms of functionality, these two groups of neurons are equivalent. And in this case, we say they are learning the same representation, or they form an exact match. Our definition for exact match also works for convolutional layers. We just need to replace the output of the neurons by feature maps and replace the weights by convolutional filters. So this definition has an equivalent form. That is, the output of these two groups of neurons span the same linear subspace. Formally, suppose we have test examples A1 up to AD, and we say the output of a neuron X on these test examples form a vector called the activation vector. If the activation vectors of two groups of neurons span the same linear subspace, we say the two groups of neurons form an exact match. And if the activation vector for every neuron in each group is epsilon close to the linear subspace spanned by the other group, we say the two groups form an epsilon approximate match. Under our definition, matches are closed under union, so there is a unique maximum match, and we define simple matches to be matches that are not the union of smaller matches. And we can show that any match is a union of simple matches. We also design algorithms for finding the maximum match and the simple matches to conduct experiments. So in our experiments, we plotted this figure showing the size of maximum match divided by the number of neurons for different layers. As you can see in this figure, we found few matches in intermediate layers, which suggests low similarity in intermediate layers. If you want to know more, come to poster number 26. Thank you.
Our next spotlight talk is going to be presented by Jilu Zhang. This talk is titled Generalized Cross-Entropy Loss for Noisy Labels.
Hi, good afternoon, everyone. My name is Zilu, and today I'll be presenting to you about our work on generalized cross-entropy loss for training deep neural networks with noisy labels. Deep neural networks have achieved tremendous success in numerous tasks. However, they often require a large amount of clean labeled data, which can be very expensive to obtain. Moreover, it has been recently demonstrated that training neural networks with the widely used cross-entropy loss can lead to a significant overfitting to noisy labels. In light of this, we propose a loss function for training neural networks for noisy labels. As a background introduction, a loss function is symmetric if the sum of losses with respect to all ground truth label classes is a constant. It was previously shown that symmetric loss can be tolerant to noisy labels. Mean absolute error was thus proposed for training neural networks with probabilistic output in the presence of label noise because it's a symmetric loss function. On the contrary, the widely used cross-entropy loss is not symmetric. However, despite the theoretical guarantees, mean absolute error can lead to poor performance of classification accuracy. To see this, we empirically examined the performance of mean absolute error against cross-entropy using ResNet on CFR10 for clean labeled data. The orange and blue curve shows the test accuracy against number of epochs for both the cross-entropy and mean absolute error. Not only does using mean absolute error lead to a much slower convergence, but there is also a slight decrease in test accuracy. The phenomenon is much more significant when using more difficult data sets like CIFAR100. Using mean absolute error, the highest accuracy achieved is around 38% in 2,000 epochs, and cross-entropy achieved a much better performance after 7 epochs. On one hand, we have cross-entropy loss, which has good convergence properties but prone to label noise, and on the other hand, we have mean absolute error, which is more noise robust but have bad convergence properties. In this work, we propose to use the negative of Box-Cox transformation as a loss function. What's resulting is a set of loss functions with a parameter q. When q is set to be 1, it is equivalent to mean absolute error with probabilistic output, and on a limit of q equal to 0, it is equivalent to cross-entropy loss. Although LQ loss is not symmetric, it has bounded sum of losses for non-zero q's, and the larger the q value, the tighter the bound. In this work, we showed that the tighter the bound, the more noise robust the loss function. However, larger q is not always preferred. To see this, we empirically examined the behavior of LQ loss with various values of q using ResNet on CFR10 with manually injected noise. The curves show the plot of test accuracy against the number of epochs. As seen clearly from the orange curve, when trained with cross-entropy, the model starts overfitting very soon. Training with increased q values delayed overfitting phenomena so that more useful features can be learned and higher accuracy is achieved. However, if too large of a q value is used, the model converges too slowly. Hence, there's a trade-off for optimal value of q, and empirically we found that q equal to 0.7 has been effective for all our experiments. The optimal q value can be found by cross-validation. Recall that the loss functions with more bounded sum of losses lead to a more noise-robust loss function. Based on this observation, we also proposed the truncated LQ loss function, which lead to tighter bound and hence more noise robustness. The truncated LQ loss is essentially the normal LQ loss if the probability output is above a certain threshold k and a constant otherwise. In practice, we used alternative convex search algorithm for optimization with the loss function. Lastly, we empirically examined the performance of a proposed loss functions using ResNet on various data sets with manually injected noise and achieved consistent improvement over both cross-entropy and mean absolute error. The bar charts on the right illustrates a small part of our result. Thank you very much for your attention, and I hope to see you at our poster number 101.
With that, we've come to the end of the session. I'd like to thank all the speakers and the attendees. And in particular, I'd like to thank Chinmay Singh from Microsoft Research and Michael Uzzolino from University of Colorado Boulder for helping keep things on time. Thank you all.